So, hello everyone. This is the English version in case I absolutely have to give the talk in Portuguese. This is the English version of the presentation for Ciência das Alterações Climáticas, where I will talk about what to learn from ocean color remote sensing as an essential climate variable and the lessons that we can learn from Greenland's ice sheet, from Greenland's ice loss. Ice loss should be understood here as both loss of sea ice in the seas around Greenland and also the loss of the mass of ice sheets. Here you can see a very good artistic view of the Sentinel-3A that was launched by ESA almost 1 year ago in February, taking a picture measuring this algal bloom in the north of Norway, at the north of Norway. I will give a very short introduction on the importance of Greenland and what is also the climate change initiative. I will talk about the importance of Greenland, ocean color remote sensing, basically the physical principles of measuring ocean color from space, and try to answer the question of how can ocean color products be used in order to address climate change studies. Then I will talk about the data methods that I have used, some results, and future work. I would like to start with a little bit of philosophy. Professor Shel Nuber from the Peak Institute in Potsdam, Germany, has this very good article that I really recommend, where he talks about the Earth system analysis as a second Copernican revolution. Ironically enough, like in the Copernican revolution, there was science that was not very well accepted by the society. Now we have, and that science at that time was all about using powerful instruments like telescopes to look at space, and now we have much more powerful instruments looking back at Earth, providing very good evidence that our planet is needs to be taken care of. And here we have this doctor analyzing what is wrong, and actually what you can see here in this picture from that article is a thermoline current right here, so it's a very important aspect. So what are essential climate variables? The essential climate variables were actually defined by this global climate observing system that was brought on by the UNFCCC, and it's a set of physical variables that can help us understand how the Earth is changing, the Earth's climate is changing, and ESA actually have a very good response with a set of projects that we call the Climate Change Initiative, CCI. What are these essential climate variables that ESA is responsible for studying? Well, they vary from glaciers, land cover. We can actually see fires. If you remember the satellite pictures given by satellite Sentinel-2A from Madeira Islands this last summer with the fires. And they are many. I actually advise you to download this app where you can understand and you can explore these many essential climate variables and see what is the data associated to it. I will talk in my thesis about ocean color and sea surface temperature, and in this paper in particular about sea ice and ice sheets. So, Greenland is very important. 80% of Greenland is covered by ice. It is the second biggest ice sheet in the world, the first one being Antarctica. And if we would melt all the ice in Greenland, we would get an equivalent sea level rise of 7.2 meters. It is a very ocean. It is an ocean region of extreme importance because, as you know, there is Arctic amplification. We know that the sea ice is decreasing around these oceans around Greenland, so the Greenland Sea, the Baffin Bay that we will see, and since as long as this ice is disappearing and it disappears earlier in the annual cycles, there is more absorption of light coming from the sun, and so a decreasing of albedo, and the Earth as a whole increases its temperature further. Um, it is very, so that you understand this, the depth of the sea ice. Here you have the bedrock, so the continental Greenland is here, and then the ice can be up to 2.5 kilometers deep. The loss of sea ice in Greenland has been studied in many ways. Um, the most popular one is to study with this special type of radar. It's called the synthetic aperture radar, but you can also measure with radiometers, altimeters, and optical instruments. You can look at the glacier front and understand how it's receding in time. So we can also, because these measurements are so precise, we can also understand what is the cumulative sea level rise. So with the loss of ice in Greenland, how much is the sea level actually rising to that equivalent mass? And of course, the melting season in Greenland is increasing, so we have more days of melting than before. Here you have an average for 79 2007 and here in 2012. So there are more days in which the sea ice, the ice sheet is melting. What is very interesting to understand is that another way of looking at this ice loss is through gravity. There are satellites that can pass over Greenland, and these missions, they were conceived to study gravity, study the tiny details about gravity, but they can also measure the loss of ice because these satellites get less, they see less pull, they feel less pull from the gravity of the Earth because this huge mass of ice is disappearing. That is very interesting to understand. The ocean color works in a completely different way. It is basically the sensing of in visual light, so visual with the visual part of the spectrum, the visible spectrum, we can see the greenness of some surfaces. Actually, the chlorophyll is the only biological parameter that we can detect from space. Here you have the absorption spectra for the chlorophyll A and chlorophyll B and keratin, and they all have, they reflect more. So here is the absorption, here is the reflectance. They reflect more in the green and the yellow part of the spectrum, and they absorb more in the blue and in the red. So when you divide the reflectance from this part of the spectrum to this part of the spectrum, you get a very good correlation with chlorophyll content. So it is via the reflectance ratio that you can understand the content in chlorophyll. And of course, for terrestrial plants, then that means more plants, more trees. But for the oceans, the equivalent is algae, these phytoplankton cells. The data that we can retrieve from these techniques has been operational since 1997 with SeaWiFS, that was launched on board of the Seastar satellite, as it is called. And so we have 19 years of operational data, and we can understand how these algae are growing, what is all the dynamics, and it's very important to understand that they absorb 50 gigatons of carbon per annum globally. So they absorb as much as terrestrial forests in 1 year. So my research question is, how can these ocean color products be used to address the climate change studies? We will look in two ways. We will look to offshore areas where the Arctic sea ice extent is decreasing or it's melting earlier in the year. And so what signal can be extracted from these ocean color products when the sea ice disappears sooner for the same reason? From the same season, sorry. And the second part of the question is, are phytoplankton cycles change in the coastal areas near these outlet glaciers because there is more meltwater coming from the glaciers and delivered to the sea, and this water has some nutrients, some inorganic nutrients that are used for phytoplankton growth. The data that we used is very big. It's a huge amount of data. We have collected means of 5 days. So 5 days products of chlorophyll A and another coefficient that I will talk about further. And this corresponds to these 431 gigabytes of data. You can see these projects changing. Here you have chlorophyll concentration, here you have Greenland, and what you see in white are areas in, so that you understand the difficulty of this problem, is that you can have either night, so if you don't have sunlight, you don't get a reflectance spectrum, so you cannot do this kind of analysis, but you can see the clouds. If it's cloudy, these products are also impaired by clouds and the presence of ice. When there is ice, we still have no data because basically there's no water. There's no water surface actually. We have also used the OCCCI portal. So for the first question, we really need the map, so we really need the whole of the data. And for the other part of the question, since it's more localized with this portal that is maintained by the Plymouth Marine Laboratory, we can look at a region, a specific region, and directly download data from here. And then I used signal analysis, like the wavelet transform, with the mother wavelets, Morlet. Our region of interest, so I have selected here two offshore areas, A and B. We have the Baffin Sea and the Denmark Strait. And then we have these these three glacier systems and the southwest strip, which is in the middle of these two environments. So what is the state of the art? The IPCC has very good data. It sums up a very good amount of data about these changes in ice. So here you can see that for winter and spring we normally have ice in the Baffin Sea. That then disappears in the summer and autumn. But in the summer and autumn, there is a decreasing trend of ice concentration per year. So basically the ice disappears sooner in the year, and that relationship has been already approached by this very good article that actually had an impact on the popular press in Washington Post, actually quality press if we can call it. It was written by Matti Karhu and Van der Brouwtes from our faculty of Science in Lisbon, and it has related some spots where with the disappearance of ice, with the melting of ice sooner in the year, the chlorophyll concentrations are also appearing earlier in the year. So the results of mapping these Changes in the occurrence of chlorophyll concentrations are here. We have here an animation. I have actually imported this data into MATLAB, and here you can see how it changes through the years. What is the basically what this animation shows is what is the day of the year in which we have more chlorophyll abundance, and this day is sooner in the blue areas and later in these yellow and red areas. I have created maps, a medium and a mean day of chlorophyll maximum. So when you see here 175 is June 21st, and here we can have phytoplankton bloom, so the peak of the chlorophyll is higher later in the year and sooner in these regions. And we know, as you will see, that this is related with sea ice. So as sea ice disappears earlier, as we have here for the Baffin Sea, here is a graph of how the sea ice extent was varying throughout the years. Here is a threshold of 15%. It's a threshold that we normally use, and I have calculated in which days is the ice less than 15%. So it increases during the winter and decreases in the summer. And so what is the day around the summer where we can see that the ice concentration was less than 15%? And if we collect all this information from 1997 to 2013, I didn't have more data for until 2015, we can see that there is a trend of decreasing days in which we have a nice concentration less than 15%. And because this ice is melting sooner, it basically means that the sea ice is disappearing sooner for the same season, then we have phytoplankton growth also earlier in the year. It is very important to understand, if you remember that map, that sometimes that was for the Baffin Sea. But in other regions, and that is still to be better understand, it can occur later, even later. And we there is still some more research that we can do about it, but we think that this is related with different dynamics of the transport of nutrients around these areas. If you are in the west coast of Greenland, then these nutrients get concentrated here and pushed up to the Baffin Sea, whereas in the east Greenland, the meltwater actually travels longer westwards, and this is where we have more we have a strong increase in phytoplankton abundance occurrence. So basically there are areas that are the areas where the ice melts earlier are areas where we can see phytoplankton appearing earlier also. For the wavelets in our coastal areas, we have seen that there is a shift. There is a shift in periodicity. We have marked here in white the periods of 12 months and 6 months, and there is actually a shift. So we could see that there is a cycle, there is an annual cycle of phytoplankton growth in these coastal areas next to the fjords. But this annual cycle is then substituted by a smaller period. So instead of having just annual peaks, there is a second peak that still existed before but becomes more predominant with the years. These black contours are the confidence level of 95%, so we can really say that there is that phytoplankton growth can occur instead of just once, it can occur even twice in the year. That's what basically these graphs mean. And of course, we have looked at this KD coefficient, and this is a very important byproduct of ocean color. It measures the absorption coefficient in the water. It's normally related with sediment plumes that you see here. So the water comes, the meltwater comes from these outlet glaciers or these tide water glaciers. Tide water glaciers are connected to the tide, so they are connected to the sea, and they transported these organic and inorganic particles to the sea, and this you can see through this coefficient of absorption at 490 nanometers. And this coefficient has been increasing, and there is much more variability of this coefficient later in the year. It's also very important data that explains a little bit the phytoplankton growth in two different seasons instead of just one. It is important to know that this is a way of indirectly measuring that more nutrients are transported towards the sea. So for future work, actually the conclusions first, we know that ocean color is a very important essential climate variable that explains the changes in many biogeochemical processes, and other derived satellite products can also be used, like the attenuation, the downwelling attenuation coefficient that I just talked about. Changes in chlorophyll abundance are coherent with both melting of sea ice and increasing nutrient-rich meltwater from the glaciers, and further techniques will be developed in order to maybe publish this paper and provide better quality results. I have to see the interpolation. I didn't talk about interpolation here, but there is some interpolation, and we will address that topic later. Further studies are also needed in order to understand. There is a lot of literature right now, but this is a very hot topic. So what are the variations in meltwater runoff, sediment plumes, and phytoplankton plumes? So these three vertices of a triangle are very important. Thank you, and please contact me for any questions.